Okay, people is just jumping in. I need to unmute some noisy people. Okay. Well, we can start this last seminar of the current semester. And before I start the seminar, I just to invite everybody to the General Assembly of the group. The Rock Glacier Inventories and Kinematic Initiative will have the General Assembly, the first one, in 2 hours from now. So it will be at 16:00 Central European time. You have the link in the mail, so please attend the General Assembly and participate of the current developments of the group. Saying that, today is a pleasure to me to introduce you to Sebastian Buchelt from the University of Würzburg in Germany, current PhD in the last step of finishing his PhD, presenting today detecting a small-scale patterns of rock glacier surface kinematics in the Central Alps using the DInSAR time series. So Sebastian will talk for around 12 to no more than 20 minutes, and then we'll have 5 to 10 minutes of questions after the presentation. So the floor is yours, and thank you again, Sebastian, for participating in the seminar series.
Thanks for the introduction, Sebastian. Can you hear all well? Great. Okay. So before starting the presentation, I would like to take the chance to thank especially my supervisor, Christoph Kneisel, for the support, as well as also my colleagues who took also part and partially led the fieldwork campaigns that we did, which will be also part of the presentation today, as well as Jan Blöte, who provided me with some reference data for validating the velocity information. So starting first with a short outline. So I will shortly go through methods of rock glacier kinematics and talk very shortly about why I'm using differential SAR interferometry, and then derive my objectives, and then the rest is kind of like will be quite clear, I think. So rock glacier kinematics, we have observed this acceleration in many rock glaciers, and of course it's interesting to see how it's developing, but I do not want to go into detail. I think all of you kind of know this general setting here, but they are basically affected by increasing temperatures, as well as is said to be by varying liquid water content. And they are also affected on different temporal scales, so long-term, multi-annual, and also seasonal variations. That's what we observe. Methods that have been used are traditionally like in situ measurements, which such as GNSS or inclinometers, which have the big advantage that they provide continuous measurements, but as they are usually just one plot or 1 point or several points, let's say, they have a very limited spatial coverage. And on the other hand, we have well-established feature tracking approaches, but especially when we want to derive high resolution acquisitions, especially also in time, they come along with very time-consuming UAV acquisitions, which can be quite challenging, especially in mountainous regions. And also still, we usually have a kind of limited spatial coverage along with that. So differential SAR interferometry has become kind of like the key idea to compensate for some of these issues. So it's basically using the phase difference between two acquisitions of a satellite-based sensor. It's quite commonly now used with Sentinel-1, but also other SAR satellites such as TerraSAR-X or Cosmos SkyMed, to derive information about the deformation of the surface. However, so it's coming with big advantages because of its high spatial temporal resolution and its large spatial coverage. However, so far has been mostly used for large-scale detection and inventory of rock glaciers, where it's very, very helpful. So that we can definitely say, and also partially to quantify for annual surface kinematics, usually on the scale of entire rock glacier units, and mostly based on a selected set of interferograms. So the main objectives or the gaps that I've figured out that are still there is, first of all, that I want to try to quantify displacement using the entire time series data, not just a few interferograms, but really getting the information of the entire time series that is available. And as well as that, try to analyze patterns within rock glacier units, which hasn't been done so far. Usually it's, as I mentioned, on entire rock glacier units. To get like this activity, the velocity rate. And we also then started to compare our results with results from geophysical surveys, because we realized that there might be some links between the dynamics that we observe or the kinematics of the surface that could be potentially be explained by variations in the subsurface. So basically what we do in our method is to collect all Sentinel-1 data. So it's approach based only on Sentinel-1 data, but due to the large spatial coverage and the good temporal revisit time, and process this data with an open source based approach to derive a so-called line of sight displacement time series usually on a 6-day basis for the summer snow-free summer months, except for occasional snowfall events. Then we bridge them with larger temporal baselines. And in winter, usually we don't get any information, or winter and spring season, as long as there's snow cover, there's no information in general. And then we combine the descending and the ascending line of sight displacement into an annual displacement value to kind of like stack the data and reduce artifacts that still remain in the time series, and do a decomposition of this line of sight displacement, which is figured here in the sketch. So we have line of sight displacement in descending orbit and in the ascending orbit. And by that, we can derive then the displacement component in a simplified geometry in the east-west direction and in the vertical direction. As we are kind of tracking objects on the surface, some of this vertical displacement could be due to surface slopes parallel surface parallel movement. So we compensate for these effects by correcting with the horizontal movement that we derive and the local slope in this direction to get then the final elevation change, delta Z here. Additionally, on this decomposition method, we also calculate seasonal measures. I will talk about that in more detail on the later slides. Basically, the next step I will show you now, first an assessment of how accurate we can detect the horizontal and the vertical displacement measures by comparing it with reference data, and then also an analysis of the spatial patterns of these highlighted black with the black boundaries, the values. So the main study sites are all located in the Central European Alps. We have one reference site in the Kaiserbergtal Valley, which is the side valley of the Kaunertal, where we have in situ UAV data for validating the horizontal and the vertical displacement. And for the other sites, we have used order photos for only validating the horizontal displacement component. And when we now look at the results, so here on the left column, you see the reference data from the UAV acquisitions, and on the right-hand side, you see the results that we derive from the differential interferometric SAR. We can see that the patterns kind of like fit quite well. We have this eastern part with more horizontal movement, and the western part, so to say, with a more vertical movement. We can also analyze that on a pixel level quantitatively, and we see that there is quite some good correlation. However, we also see that, especially in the east-west direction, if there's very high velocity rates, they kind of like lose the sensitivity. It's also what we observe here when we look at the values. Usually that's because we have some phase unwrapping errors, especially in very fast-moving areas, also been observed by other studies. Another example over here, we can see again, we have quite some good correlation until here, annual movement rate of about almost 1 meter, and above that we see this kind of loss of the phase information. And again here, the spatial map of those two values, you see the highest moving area here, we have a less of sensitivity. One more important information is when we look at the scale of the two axes, we will see that the velocity rate here in DInSAR is about only 1/3 of the entire velocity that we observe with feature tracking. That's kind of like makes sense, because when we check for the availability of DInSAR measurements, that also represents about 1/3 of the year, because this is like about the snow-free fraction of the year where we can acquire differential SAR interferometric data. So to say, the values are kind of like making sense, and especially spatial extent and outline is fitting quite well. But now the big advantage of the data is that we can also get some seasonal information about the velocity throughout the snow-free summer period. And I think most of you might know this area. It's the rock glacier in Valmorail. And when we look now in the different parts of the rock glacier, we see, for instance, in the lower, a strong annual variation, but throughout the summer, velocity kind of is rather in a stable state. When we go into the middle area, we start to see seasonal increase of the velocity, especially throughout August, and the maximum in September. And if we go to the uppermost areas, there we have nearly no movement in the early snow-free period, but then a sharp increase throughout August and in the late summer months. We now try to kind of like develop a coloring scheme to make this visible, and for that we used the median movement of September as an additive color in the color blue, the early movement as an additive color in the color red, and the difference between those two as an additive color in the color green. And as a result, we will see areas with high seasonality in the snow-free summer period in this turquoise color, and low seasonality in pink, and areas with unwrapping errors in yellow. And that's what the picture then looks like for this rock glacier. So we see low seasonality throughout the lower area of the tongue. Then we have very fast moving areas where we observe phase unwrapping errors. And the more upwards we go, the more the tendency we see to higher seasonality. We did this not only for this rock glacier, but for the other sites as well. And we kind of like have this pattern also on other areas that we did the analysis on. So we also see here rather pink colors here, the lower part, in turquoise in the top, or also in this area. However, there's also signs that some areas very adjacent to each other have distinct different movement dynamics. We did then a statistic analysis. For that, we excluded the area in the Nair because it's strongly north facing, and that causes some issues with the statistical analysis, as we kind of like are insensitive to this north-south directed displacement. And also slopes seem to have not really sensible kind of like statistics. One of the hypotheses that we have is that those areas with the highest displacement rates are also those with rather higher slope. So that kind of like this kind of statistic link, especially with increased horizontal displacement, might be obscured by this phase unwrapping artifacts. But what we can see is that with increasing elevation, we usually see an increasing seasonality of the pattern. So that's kind of like fitting what we can observe here. But what we also see is in those areas where we have higher seasonality, usually we have also an increasing rate of elevation change, and it's mostly negative elevation change. So basically, those areas with a higher seasonality have a higher rate of subsidence compared to other areas. We now wanted to have a closer look on one of the sites because this kind of pattern here struck quite. We have also the results from others in preparation, but not finished yet. But this kind of like with this northern tongue here was kind of striking to see what it might be the cause for these different patterns here in the southern and in the northern part. So this is also a picture from an orthophoto and a picture from the RGIK illustration atlas. And here this area is assigned as one, I think it's unit or subunit. I'm not entirely familiar with the terms, but it's highlighted as one single area. And now, as we wanted to see what we can derive within these areas, we can see that again here we have this high subsidence area here in this part and also high seasonality in this area. So we conducted some roller long ERTs in this area as well as a GPR in the long profile to see what is in the subsurface kind of. And I will now show you like the results from this cross profile first. And first we see here the measures. I again highlighted here the movement angle. So we see this negative movement angle in the northern part of the rock glacier. And here also highlighted the seasonality. We also see here this sharp increase in the seasonal pattern of the velocity in this northern part. And when we now compare it with the ERT measurement, we see that especially this area has very, very high resistivity values compared to the more southern part. And when we now look at the long profile, going from the bottom to the top, we again see high resistivity areas in the middle and in the upper part. When we go back to this represents about this area here. So where the other profile is crossing the other one, and then also the top part. And again, these are reflected by high seasonality rates and negative displacement, negative movement angle. So our conclusion our conclusion from these results is that these different patterns are linked to different subsurface conditions. And in this special case, we argue that the area that we see here, this tongue-shaped area, might be affected by former glacial ice in this area. So that we not only have and purely periglacial dynamics there, but also a glacial sedimentary ice underneath the surface that is still remnant from there. So to conclude, first of all, there are remaining challenges to quantify absolute displacement rates with DInSAR. Because that remains a challenge because we still have the issue with phase unwrapping errors. There might be tools to reduce these artifacts, such as deep learning, improved deep learning approaches or something like that. And however, still we are limited with this observation to snow-free periods. That's definitely something that one has to keep in mind. However, we really can accurately delineate active areas with this approach and also get further information about the direction and the different movement patterns regarding seasonality. Additionally, on top to that, the movement direction and the seasonality show that on the one hand, we have distinct patterns of this seasonal dynamics. So in the front, we have rather low seasonality and a tendency towards positive movement angles, whereas in the root zone, we have rather increasing seasonality and a tendency towards negative movement angles. Also, some of these movement direction patterns and seasonality are probably linked to variations in the subsurface properties, and therefore we think that especially if we expand this to other sites, that we might get some more systematic understanding that they are probably linked to different morphological origin, and this could lead to a better understanding of the current dynamics as well as give better insights how these landforms will develop under future climatic conditions. So thanks for your attention, and feel free to ask any questions. I'd be glad to answer. Thanks.
Thank you very much, Sebastian, for the nice presentation. I think now we have around 10 minutes or more to talk about questions or comments to Sebastian's presentation. Either you can write it on the chat or raise your hand. I think we have something in the chat. I can read it for you. It says, Joe, thanks for your nice presentation. You mentioned that the velocity magnitude from DInSAR is 1/3 compared with the UAV results. Can you repeat the reason? Have you compared your results with TGS or GPS measurement results?
Thanks, sure, I can do that. So basically, maybe let me go back to the slide of the results. The basic challenge that we have is that differential sinothermy doesn't work when the surface composition is changing between two acquisitions. And that's usually the case when we have snow coverage. And in these areas, in the high higher elevations of the Swiss Alps, let's say the snow coverage is about 2/3 of the year. And the snow-free period usually ranges from June until end of September, between June and July and until September, October. So we have about 1/3 of the year where we can acquire data from differential sinothermetry. And as we didn't want to extrapolate the velocity values into the winter period because we actually have no information about that with this method, we basically took just this average velocity and then stacked it and calculated it as an annual value. And as it is just 1/3 of the year, we result with 1/3 of the actual displacement that is observed in feature tracking, as long as we have kind of like a rather steady displacement, what we also seen in these areas where we have when we have the seasonality measures. Regarding the second question about comparison with GNSS measurements, no, we actually don't have these measurements, but let's say we have basically two independent measurements that we compare here. We have the UAV results, but we have also the orthophotos where we have basically two completely independent approaches to derive the velocity rates. So we kind of like are convinced that this is that these two independent approaches show the same. Thanks.
Thank you. We have a question now from Lea.
Yeah, so thank you for your presentation. I have a question, it's actually just also for this slide here. So I'm a bit lost with the time frames. So is the time frame from the reference feature tracking and DInSAR, is it the same one or not? I was a bit lost with like the time frames and also then with seasonality.
Okay, yeah, thanks for the question. That's a very important one. So I excluded this information a little bit due to time issues. So the differential SAR interferometry time series that we're using is all data from 2017 until 21. So it's basically 5 years. And as mentioned, all winter scenes are then excluded by a coherence threshold, and all the remaining ones are going into the analysis and are stacked together. And then basically we divide the aggregated displacement that we get from the entire time series by 5, so that we get the annual displacement that is detectable by DInSAR. With the feature tracking, as far as I'm remembering correctly, we have 2 acquisitions of the order photos, and these are in this case 2016 till 2019. So the time frames are slightly different, and this could also be for sure a cause of inaccuracy, especially if we've seen that there are some annual changes in the velocity rates as well. So therefore, actually, it's kind of like a good sign that the agreement between the 2 movements is still that good, even though we have some systematic offsets that are definitely reducing the quality of the results. Yeah.
Mm-hmm. And also then for seasonality, I guess it's also again over the same period, like this average is one now between 17 and 2021. Did you have a look at like if there's any variation between the years and not like within 1 year, like if one differs from the other, or did not really have a look at this?
So far not. So when we look at this kind of sketch, this is so to say,
you have the years, yeah.
Something where there's a lot of information and we still haven't exploited everything that's in the data. So what one can see here is this is like really the individual acquisitions with some filtering. Some dates are filtered out because they are clearly outliers. Still in this, there might be some as well, like these ones, which are maybe slightly affected by phase unwrapping. So on the annual changes, we haven't had a look yet, because our main interest is really rather more like the seasonal pattern that we can observe in the data, because that was something that was like on the first sight very, very interesting to look at, because no one else has done something like that so far as we know.
Yeah, so I missed that there were actually different years in this plot. So yeah, thank you. That also already answered my question a bit. But yeah, thank you.
You're welcome.
We have now a question from Andrea.
Yeah, so thank you very much for your presentation. Sorry to go back to the same question as before, to the velocity issue, because I don't know, maybe I misunderstood something. So I would expect that if you analyze only the data over the summer, which should be the period where you have probably the highest velocity, and you compare to the feature tracking that is smoothed somehow over 3 years, I would expect actually the opposite, that the DInSAR will get much higher velocity than the feature tracking. Am I wrong?
That was also something that we would have expected. So let's maybe go back to the slide again. That's something that also we would have expected actually in the beginning. So that's a really good question. Why don't we see this that it is faster? So basically what we see here is that we So we just, the thing is that we get 1/3 is just basically a calculation measure. So I could also just get the mean velocity of the summer period and then extrapolate it, then I would get rid of this factor of 1/3. That's basically just a calculation measure that we use here. Still, when we compare the data, it looks like the DInSAR is slightly lower, or at least slightly below the area compared to what we see from feature tracking. In these areas where we have highest velocity rates, this is due to the phase unwrapping errors, where we just lose one fringe cycle and the information is gone. I think also in these areas here, still we might have occasional phase unwrapping issues. So that's kind of like probably one of the main reasons why the velocity is lower than we would expect. On the other hand, still one remaining question would be for these lower velocity areas, why they aren't like kind of like set higher. I think it might be due to the fact that we have different time frames here, that they might cause different, we have basically different temporal baselines with different mean annual velocities. They might shift a little bit. It's something that, yeah, it's a very interesting question. It could also be a sign that, especially in this rock glacier, for instance, the horizontal movement might not be so much affected by seasonal variation at all. That's also something that could be a potential explanation, but to be honest, we don't really have a clear answer to that yet.
Okay. So if I may, another quick question. So just because you concluded that with this methodology, you still have some problems to understand the temporal evolution of the rock glacier due to all the facts, so the phase unwrapping and all the problems that are intrinsically related to the InSAR. But what would be then the advantage compared to using only interferograms? Because in the end, what you get is the spatial distribution that you could get directly from single interferograms or just from a stack of interferograms. So could you comment on this?
So by experience, I would say if interpreting single interferograms itself can be quite complicated. So it's quite a challenge to like outline it. And especially if we see this, what we observe is that we have the seasonal variation, the selection of interferograms also would affect your result. So for instance, if you take one acquisition that is more in the late summer, it would show different activity, let's say, or kinematics than the one that you derive from an early summer acquisition. So basically we try to get rid of this uncertainty by just predefined selecting a single image, but using all the information that's there. Of course, it's making it more time consuming because the processing is much more demanding. On the other hand, the results that we get are getting way more robust because we get having information from much more time steps. And on the other hand, especially this information on the seasonal variation would not be possible by just looking at single interferograms. And this is some information that you only get when you basically process the entire time series.
Okay, thank you.
Thank you. We have another question from Jan.
Yeah, hi everyone. Hi, Sebastian.
Hi.
So coming back to the comparison with GPS, I just want to mention that it's something that's highly discussed in the past years to find a good relationship between, on the one hand, we have few permanent GPS stations with very high temporal resolution. There's these terrestrial surveys, and then there's all the other remote sensing camp. Yeah, all the way to what you showed in InSAR, and understanding the relationship and sensitivity and what data products we should really construct is very crucial to fielding this new ECV. So that would be super important for not necessarily you, but just for people to really get involved quantitatively. And the other nugget I want to say, there are a few select sites, not necessarily just on rock glaciers, but on moving terrain, where even there are corner cube reflectors, or there have been over some periods in time, yeah, as enhanced markers to be used for SAR, yeah, or to figure out whether they can be used. So the one site I know best was for terrestrial InSAR, but they should also be visible in space-based InSAR. Yeah, I could point you or anybody else to that. Yeah. And if anyone's interested in very high temporal resolution GPS, me and I guess also Julie, who's listening in, who I see here, are very eager to help and to talk. Yeah.
Thanks for the recommendation. I think there's still a lot more to figure out, and also to like get the numbers right. But at least for us, let's say the quantitative measures, I think that's also something that also in discussion within differential star interferometric community is kind of agreeing on. Getting the absolute numbers is kind of like a challenge, but for relative values, it's really, really helpful. And that's something that I'm also trying to show here, that this relative acceleration in the season is something that could be very helpful, but for better understanding. But also we still see this relative changes also like here in this figure on the left with the annual changes, which we have not used at all for our analysis.
Yeah, so what I really took home from your presentation here and this piece of work is a rather systematic approach. Yeah, to just I mean, it's of course it's just a shot out at the community with these categories that you were showing, and that this interpretation method that you have been proposing, and that's really important. Yeah, not just plot away and look at it.
Thanks.
I think we have a last question. It's written on the chat. I can read it for you. It's Veronica. She says, thanks for your presentation. I have a question about the DInSAR processing. Have you considered to use different time series techniques such as SBAS? What do you think will be the difference between this technique and the stack you applied?
Yeah, that's also a good question. In the beginning, I was trying out a little bit on that, but I went very fast away from trying to use SBAS or any kind of this method, because let's say a combination of different interferograms of different time lengths, because I realized that already with 6 days interferograms in some sites, I run into issues with phase unwrapping, and this would get much more if I use also longer temporal baselines. So therefore, the conclusion I've been drawing was just sticking with the 6 days interferograms is, let's say, working better for these kind of velocity rates that we observe here. It really depends. If we have a very slow moving feature, maybe SBAS might be better, because then we are compensating better for atmospheric artifacts or other sources of errors, which we do not, or we do less compensate in this approach here. On the other hand, by using a distinct set of interferograms, we kind of like can reduce this effect of the arbitrary effect of the phase, because this is basic. The atmosphere is more or less the influence of the artifact is basically distributed randomly. And if we aggregate a lot of scenes, especially for these stacked seasonal measures, we kind of reduce these random artifacts compared to just assessing individual interferograms.
Thank you very much for the question. I think probably there's no more questions from the public or in the chat. So, well, I want to thank you again for the presentation and all the participants to exchanging in deep comments. So please, I think they can contact you. They have more details.
Sure, definitely.
Yeah, keep the conversation ongoing about this interesting topic and the results of your study. I would just want to remind you that in an hour and 20 minutes we have the General Assembly, so you are all invited to attend. And I think we have some representatives here from the ExCom committee, like Cecil. And yeah, probably they are too busy preparing the General Assembly. So yeah, Cecil is here. You want to say something?
Yeah, I mean, just quickly for the people here. So the General Assembly is basically will be information about this transition that we're on. And as you should all know by now, there will be a vote and election next week. So it's a bit of preparation of this. That's why we called for a General Assembly to explain a bit what's going on. Yeah.
Thanks.
And I think the link is the first to the meeting is also the first comment in the chat if you haven't received it yet.
Yeah, so the invitation is already made. So I will see most of you in a few hours, well, less than an hour and 20 minutes. And thank you, Sebastian, for the presentation. And if the last thing will be, if somebody wants, we have still one spot available for the next semester. So if somebody wants to present his or her work, please contact us to book you a time slot for presentation. So thank you, everybody, and see you soon.